This is part 3 of chapter 14 lecture. This part is going to be dedicated exclusively to buffers, buffer solutions. Very important, especially for those of you who are going into nursing at all. These are important. And it's important for us to know as well because buffers are important in our body, in our blood specifically, and therefore it's good for us to know what's happening in our body as well. A buffer solution is a solution that tends to maintain the pH it has because it neutralizes added acid or base if they're in small amounts. And this is added acid or base, not the base or an acid that's present in a buffer solution. This is if I add more to it, more acid or more base externally, it acts to neutralize those small amounts of added acids or bases. This is perfect in our body because we're constantly producing H plus or OH minus ions in many chemical reactions that are occurring in our body, but we need to maintain the pH of the blood as constant as possible because then we wreak havoc, and that's why we have a buffer system in our blood. How do we need to have, so the buffer solution needs to have an acid present to react with any OH minus that is added, and it also needs to have a base which needs to react with the H3O plus added. If they're added, well, they don't both have to be added, but if I add an acid, it has to have a base to react with it. If I have an OH minus, it has to have an acid to react with it. If I were, so let's look at this picture here. If I just had a pH of 7 in a glass of water, pure water, I have nothing in it, and remember we said that pure water has a neutral pH. It's 7, pH 7. If I add even small amounts of H3O plus to that water, you will see that the pH is going to drop very drastically because there's nothing in that solution to react with H3O plus concentration that I added. And because the pH value is directly a measure of the H3O plus concentration in solution, whatever I add is going to lower the pH. It's going to make it much more acidic. The opposite is true, obviously, for an OH minus. If I have pure water and I add OH minus, then the pH is going to shoot up because now I have a lack of H3O plus ion, or I have an excess, if you will, of OH minus ions, which brings the pH up. And those changes, because I have nothing to cushion those changes, are very large. So if I add even small amounts of H3O plus, I go from a pH of 7 down to a pH 4. Same thing with the OH minus. If I add even little amounts of OH minus, I go from a pH 7 to 10.5. Boom, just like that. Well, this is a very good, like we said, for our body, for example, because we have to have the blood at a pH as close to 7.4 as possible, which means that even little fluctuations in H3O plus or OH minus, if it weren't buffered, would make huge differences in pH, whether lower it too much or increase it too much. Therefore, this would cause a lot of issues in our body. Now, here's a buffer solution. In a buffer solution, I have an acid and a base. I don't just have pure water. And therefore, if I add a little bit of the acid, so if I add extra acid to whatever is in there, the base that is mixed in the buffer solution is going to react with H3O plus. And the pH is going to change very little. Look at it, from 7 to 6.9. Very small pH change. Now, if I add OH minus, the same idea, the acid in that solution is going to neutralize the OH minus that is being added, and the pH is going to increase very little to 7.1. This is the difference between a buffer solution and a pure unbuffered solution. The pH for the same amount of added, right, we're adding the same amount of H3O plus or the same amount of OH minus for both solutions. But for the unbuffered solution, the pH change is drastic. For the buffer solution, the pH change is minimal. And that obviously this is what we want in our body. So let's take a little closer look at how a buffer works to try to understand why the pH doesn't change so much. Buffers, then, these solutions work because they resist the changes in pH, and they do that so in our body they absorb H3O plus or OH minus from cellular processes, from foods that we break down, etc., to maintain a constant pH or as close to a constant pH in the blood as possible. They are therefore very important in proper functioning of our cells and in our blood, because if the pH changed so much, for those of you who have done any biology, what happens when pH changes, you destroy proteins. Proteins have a very narrow pH range that they operate under. If that pH is changed, whether higher or lower, we call that denaturing of the proteins. The proteins will unravel, they will be destroyed, and that, depending on how widespread that is, you could destroy a cell, you could destroy a cluster of cells. So there's a lot of damage you can do by changing pH. And buffer solutions work to maintain a pH of 7.4 in our blood, which is very important as well. Obviously, a change in the pH of the blood will affect the uptake of oxygen from the lungs and other cellular processes. So it is very important that our pH stays as close to 7.4 as possible. This is, once again, I have tailored this for those of you who are going into nursing because buffers are critical in our body. So here's the components of a buffer. The buffer solution is a solution that contains same concentrations. So the concentrations of a weak acid and its salt have to be present in equal amounts. It has to be a weak acid and its salt, meaning its conjugate base. Okay? So here's my weak acid. This is for the blood, so I've taken this example to illustrate a buffer. This is our buffer system in our blood. It's the weak acid, which is carbonic acid, and its conjugate base, HCO3 minus. And I said salt because it could be paired up with the sodium ion here, so which forms a salt because you have a positive ion and a negative ion forming a salt. But the important part that you need to absolutely remember, the components of a buffer are a weak acid and its conjugate base. These two are related because this is my weak acid and this is the conjugate base that is formed when that proton leaves the acid. So they both have to be present, and they both have to be present in equal concentrations. That is what makes a buffer. Not that I just have a weak acid, not just that I have a base, but they both have to be present, and they have to be present at equal concentrations. In that carbonic acid buffer that we just mentioned, and sodium bicarbonate, HCO3 minus, what happens? Well, if I have sodium bicarbonate in water, it will split into, completely dissociate into HCO3 minus and Na plus. Sodium ion here is just a spectator ion. It's called a spectator ion because it doesn't do anything. It just is there. That's why it's spectator. It's just watching. It doesn't participate in any of these reactions. So the salt, this salt, is added to provide the higher concentration of the base, HCO3 minus, than if I just have the dissociation of the acid alone. So if I put the H2CO3, if I just had this in solution by itself, it will dissociate a little bit to form the conjugate base, but very little. So because it's a weak acid, we don't have 100% ionization. This will not split 100% into this conjugate base and H3O plus ions. It actually splits into these two ions very, very little. Most of it will remain as the weak acid, H2CO3. To make these concentrations equal, that is why I add the base, the bicarbonate ions. I add these ions to increase this concentration to make these two equal to each other. Okay, so I have to have concentrations, equal concentrations of both of these in my blood. Now, how does this work? How does the weak acid in a buffer work? How does it function to neutralize a base? Okay. If this is my carbonic acid, this is my weak acid, I am not, for the moment, I am not looking at HCO3 minus. I'm just looking at my weak acid. What happens if I add a strong base to it? What happens if I, from a cellular reaction or something else, breaking down a food, I produce some OH minus ions and they are dumped into the blood? What is going to happen? So for right now, I'm ignoring the HCO3. That is right? I have H2CO3 and HCO3 in equal concentrations. Now I'm adding some OH minus to the initial concentrations of these two. This is my buffer system, and I'm adding a little bit of OH minus. Well, I know that this OH minus is not going to react with HCO3 minus in that solution, but it is going, because this is a base, and this is also a base. So, so this base is going to react with my acid. What is carbonic acid going to do? It's going to neutralize that base. It's going to react with it to give me water and a little bit of bicarbonate. A little extra, not the initial, but a little more, because now it reacted with the OH minus that was added to produce more bicarbonate and just water. So effectively, it neutralized the OH minus. It took care of these ions because it produced water and a little bit of its conjugate base. So when I add an extra strong base to my initial buffer solution containing equal amounts of these two, what happens is the OH is going to be neutralized. I'm going to use up a little bit of my acid, and I'm going to be producing a little more bicarbonate. So the bicarbonate goes up a little bit, the acid goes down a little bit. This is the scenario when the OH minus is added. When the OH minus is added, my initial concentration of the weak acid goes down a little bit because it is consumed with a base that's added, and I produce a little more of the conjugate base, so that concentration goes up a little bit. But the change isn't drastic, and so the pH change is not going to be very drastic. It's just a little bit, I have a little more base, and that therefore it's going to be a little more basic than it originally was. So it's going to be maybe a 0.1 change in pH. So as I had it earlier, from 7.0 to maybe 7.1. Or if this is in my blood, from 7.4 to maybe 7.45, etc., etc. So just a slight increase in pH. Now what happens if I add acid, extra acid in solution? Okay, here is my initial concentrations of my base and my acid, right? This is my weak acid. This is its conjugate base in that buffer solution. Now what happens if I add H3O+? Well, H3O+ is not going to react with my acid because these are both acids. But what is going to happen is going to react with its conjugate base, right? I have an acid. It's going to react with a base. It's going to neutralize the acid to make water, and it's going to form a little more carbonic acid. This is what's going to happen, right? It's going to accept a proton from the acid to turn into carbonic acid, and then this remains water. So when I add a little acid to my buffer, it's going to react with the conjugate base to form a little more of the acid and then neutralize it as water. Therefore, the H2CO3 concentration goes up a little bit, and the HCO3 minus concentration goes down a little bit because it reacted with H3O plus. It got consumed, a little bit of it got consumed. Therefore, when I do add H3O plus, because I have an increase in my acid concentration, I have a little bit of an increase in, or a decrease in pH. For example, from 7.4 in the blood, it might get to 7.35. So just a very minimal increase because I have both of these components present. And now you can see why it's so important that I have the weak acid and its conjugate base in the same equal concentrations to be able to withstand the addition of extra acid or extra base to the buffer system. Not only is that important, but the amount is also important. The stronger, the higher the concentration, the better buffering system is. So a solution that is only 0.1 molar in H2CO3 and HCO3 minus, it is much weaker, 10 times weaker than a solution of 1 molar H2CO3 and HCO3 minus, because there's a lot more of it to withstand the H3O plus, right? If you think of the molar concentrations being moles per liter, in 1 liter, if I have 1 molar solution, I will have 1 mole of each of these. But in 0.1 molar, I have 0.1 moles of each of these in 1 liter solution. So I have less, the more dilute the solution is, the smaller the concentration, I have less of these weak acids and conjugate bases to react with extra acid and extra base. Therefore, it's not as efficient of a solution as the one that has higher concentrations. So if I have 1 molar concentrations of these, that means I have 1 mole of each, which means I have a lot more to react with my acids, added acid or added base. Now, as just a recap, the buffers work because the weak acid neutralizes the base, the added base, and the conjugate base neutralizes added acid. So here is kind of the whole picture. This is my buffer. If I add acid, it's going to react with my conjugate base to decrease that concentration and increase the HCO3 a little bit. If I add OH minus to this, the acid is going to react with it to decrease its concentration a little bit and increase the HCO3 minus concentration. Those changes are minimal, they're very small, and that is why we don't get huge shifts in pH. The buffer, as you can see, is equal concentrations of carbonic acids and its conjugate base, HCO3 minus. And we just talked about adding H3O plus reacts with HCO3 minus, adding OH minus neutralizes H2CO3, the acid. Now, the pH is maintained well as long as the amounts of acid or base that are added, so OH minus or H3O plus, are added to the system, are small compared to the concentrations of the buffer. So if this concentration is very small compared to the initial concentrations of my buffer, then the pH changes are going to be relatively small. That is why I said that it's very important to have high concentrations of these in your buffer solution. If I have 1 molar concentration, but I add 0.05 molar H3O plus, that is very, very, very little compared to the 1 molar initial concentration. And that's why the changes in pH are very small. The same thing with the base. So that's the important thing. Now let's look at the practical aspect of the pH. This is the pH buffer in our system, in our blood. Okay, we have the carbonic acid in our blood and its conjugate base HCO3 minus. Now, if I have a basic substance, so if I have an OH added to my blood, that is going to react with my acid to produce a little more HCO3 minus. If I had an acidic substance, H3O plus, it will react with HCO3 minus to produce more H2CO3. Now remember that this is connected, so H2CO3 can also break down into CO2 and H2O. And if you remember from chapter 8, we talked about Le Chatelier's principle. So these reactions are all connected to each other. And if I increase the concentration of one, it's going to shift a reaction in this direction or that direction, depending on what I am using. So, for example, if I increase the concentration of H plus, what that's going to do, because I increase it, is going to try to react, obviously, with my base, my conjugate base, to get rid of that H plus according to Le Chatelier's principle. And as it reacts with the HCO3 minus, as it reacts with H plus, is going to form H2CO3. Well, this is going to affect this reaction over here. If I increase, this is now a product. If I increase this, it's going to shift the equilibrium towards CO2 and H2O. So H2CO3 is going to break down to CO2 and H2O. The opposite is true when I have OH minus, right? OH minus is going to decrease the concentration of H2CO3 in the blood, which is going to shift this reaction towards making more H2CO3. So it's going to combine the CO2 and H2O to form H2CO3. There are two medical conditions that describe the pH in the blood that changes: acidosis and alkalosis. Acidosis, if you, just from the name, occurs when the pH of the blood lowers below 7.4. You have more acid, it becomes more acidic, and therefore you have acidosis. Alkalosis is the opposite. When the pH of the blood increases above 7.4, then you have the condition called alkalosis. You have a more basic blood solution than you need. And therefore, the body works to maintain the pH. If it becomes more basic, it wants to lower its pH. If it becomes more acidic, it wants to raise the pH. There are two ways that we do that in our body. If there's an increase of H plus concentration in the blood, meaning acidosis, increase of H plus concentration will lower the pH. Make sure that you kind of get that relationship because it's counterintuitive. But an increase in H plus concentration lowers the pH value. Remember, our pH value is from 0 to 14. 7 is neutral. If I increase the H plus concentration, that means I'm between 0 and 7. So I'm in the lower end of the pH scale. The opposite is true for lowering the H plus concentration or increasing the OH minus, either way. So if I have an acidosis scenario where I have higher concentrations of H plus in my blood than I need to, due to Le Chatelier's principle, my HCO3 minus is going to combine with H plus, the extra H plus to get rid of it, right? I introduce a change, I increase the H plus. The body is going to act in such a way to counteract the change, meaning it wants to lower the H plus, and it does that by combining it with HCO3 minus to form H2CO3. Once you form extra H2CO3, you increase that value. This is going to shift, once again, from Le Chatelier's principle, is going to shift the equilibrium towards making more CO2 and H2O to get rid of H2CO3. How do we get rid of the CO2? We exhale. We get rid of CO2 by breathing out. And this is a faster way to equilibrate the pH of the blood during acidosis. We exhale it, and therefore we exhale it fast enough so that we can bring the level of H plus down during acidosis more quickly than we can alkalosis. During alkalosis, we have an OH that is reacting with H2CO3 to produce HCO3 minus, increases this HCO3 minus concentration. Well, we can't breathe this out, but the way our body does it, our body is created to take this HCO3 minus concentration and to lower it. It does it through our kidneys. Our kidneys are responsible for maintaining the HCO3 minus concentration. If there's a lot more HCO3 minus concentration in the blood than it should, so I have an alkalosis type of situation, it's going to excrete, it's going to get rid of the HCO3 minus concentration as it filters the blood. If we have less than that, then it's going to hold on to it. It's not going to get rid of the extra HCO3 minus. That is how our body gets rid of or maintains the HCO3 minus in the blood to get rid of alkalosis. As you can see, equilibrating our body or the pH of the blood in an acidosis scenario is much faster than alkalosis because we breathe a lot faster than our kidneys can filter the HCO3 minus or get rid of it. However, in both of these, depending on how severe the cases are, it cannot be as simple as this exhaling CO2 or HCO3 minus. In those conditions, you might get hospitalized depending on how severe these conditions are. But this is why it's important to know about the buffers, and it's important to understand equilibria and how to understand Le Chatelier's principle and what happens when you have excess acid or base that is being added into the blood. This is the end of chapter 14 lecture. Once again, make sure that you understand, for this part anyway, part 3, that you understand how buffers work, what are the components of the buffer, that the higher the concentration of the buffer components is better than lower concentrations because it maintains the pH changes much better, and then understand how the buffer system in our blood works and how it works to get rid of the excess OH and H3O+, acidosis and alkalosis type of conditions. If you have any questions, please don't hesitate to ask me.